All right, today we're breaking down a framework that is absolutely essential for understanding the future of AI. It's called the Hardware Friction Map, and it helps explain a really big question. Why do some brilliant AI ideas actually ship while others just die on the vine as research papers? The answer, as you'll see, isn't just about elegant math. It's about cold, hard economics.
So to really get our heads around this, let's start with a puzzle from the world of frontier AI, a real tale of two models.
So picture this. It's late 2024. On one side, you've got DeepSeek V3. To get this massive 671 billion parameter model trained, the team had to spend 6 straight months rebuilding their entire infrastructure from the ground up. I'm talking rewriting cluster schedulers, building totally custom kernels, the whole shebang. Now, on the other side, you've got Meta's Llama 3.1, another monster at 405 billion parameters. And how much new infra did they need? Basically none. They trained it on the same stack they already had. Both teams were pushing the absolute limits, but one paid a huge engineering price and the other didn't.
So this begs the question, right? Why the massive difference in engineering cost? I mean, one team is doing a fundamental rebuild and the other is pretty much business as usual. What in the world is going on here? Well, the answer lies in this idea of a hardware friction map. And the key insight is this. Hardware doesn't just give you a simple yes or no on a new architecture. Instead, it imposes a tax. So what is this tax? We call it hardware friction. Think of it as the total cost in both engineering time and compute cycles that you have to pay to drag a new idea into the real world and make it work on the hardware we have today. It's not a switch that's on or off. It's a gradient of pain, ranging from, oh, that's easy, to, wow, this is going to be brutal.
Okay, so once you start thinking in terms of this friction tax, you can actually build a practical map. You can sort any new architecture into one of 4 distinct zones, each representing a different level of engineering pain.
First up, we've got the green zone. This is the sweet spot, the path of least resistance. These are techniques like grouped query attention or ROPE. They're basically clever algorithmic tweaks that are for all intents and purposes drop-in replacements. They just work on existing systems. The only real cost is the retraining. And that's exactly why these ideas get adopted so fast, usually within about a year to 18 months.
Next, we move into the yellow zone. This is what we call kernel friction. Here, an idea is good, it respects the hardware's memory, but it needs some special treatment. You have to roll up your sleeves and write some custom, low-level code. Think fancy new CUDA kernels. Flash attention is the poster child for this zone. And notice the adoption time jumps to about 24 months. That's not just writing the code. That's the time it takes the whole ecosystem to catch up and integrate it.
Okay, now things start getting really expensive. We're in the orange zone. System friction. These are the ideas that don't just need a new kernel. They break your entire serving system. You can't just pip install a fix. You're looking at a full-on distributed systems overhaul. Mixture of experts is the classic example here. And the cost? We're talking a 3-year-plus adoption cycle. Immense.
And finally, we hit the red zone. This is prohibitive friction. Let's be blunt. This is where cool ideas go to die. These are architectures that are just, fundamentally speaking, a different language than GPUs. They're not built for the dense matrix math that makes our current hardware scream. Things like CANs or neural ODEs, they might look beautiful on a whiteboard, but the cost to make them work at scale just explodes. They are, for now, economically unshippable.
All right, so that's the map in theory, but let's make this real. Let's look at a couple of case studies to see how this plays out in the wild.
So let's start with flash attention, a classic yellow zone example. The paper drops in May 2022, and everyone sees the massive speedups, but it wasn't until mid-2024 that it was everywhere. So why the 20-month lag? Was the code itself that hard to write? Nope. The real delay, the real tax, was getting it integrated upstream into PyTorch, getting it validated by the big cloud providers, and getting it adopted by all the different inference frameworks. That ecosystem tax is very, very real.
And for the orange zone, oh man, the story of Mixture of Experts is perfect. The core idea was published way back in early 2021. And then, crickets. For nearly 3 years, the idea just sat there, stuck in what the source perfectly calls Google Research limbo. It wasn't until Mixtral came along and proved you could actually package this thing up, and a ton of capital pressure built up, that labs were finally willing to pay that massive systematic engineering tax to make it a reality.
But here's the reality check on Mo. After paying that huge engineering tax, what do you actually get? Well, the marketing hype was all 5 to 7 times faster, but the reality is it's more like 2, maybe 2.5 times faster, and that's only at short context. As the context window gets longer, that advantage shrinks dramatically, down to like 1.3x. The source calls this the context trap. Mo is a throughput optimizer for sure, but it is not magic.
Now here is a really critical point. Friction is not a fixed number. It can actually change depending on the scale you're operating at. And state space models, or SSMs, are the perfect example. At the 7 billion parameter scale, they're in the orange zone. It's tough, but they're production viable. But the moment you try to push them past 13 billion parameters, the friction skyrockets. They fall off a cliff, right into the red zone, because the training penalties just become economically impossible to bear.
Okay, so why should you, especially if you're a builder, a founder, an engineer trying to make decisions, care about any of this? Well, it boils down to one thing: your resources, your runway.
Because here's the thing, this friction map is not the same for everyone. For a giant lab like Google or Meta, high friction can actually be a good thing. It's a competitive moat. They can afford to burn 36 months of engineering time to make an orange zone idea work, and if you can't, they win. But for a startup, for an enterprise team, betting on a high-friction architecture is a death sentence. You will burn through your runway long before you ever ship a viable product. It's that simple.
So to turn this from just a gut feeling into a repeatable process, the source lays out this really clever hardware friction scorecard. It's a way to systematically measure the pain. It breaks friction down across 5 key axes, everything from how well an idea aligns with the hardware's matrix math capabilities to how mature the surrounding software ecosystem is.
In using it is pretty straightforward. You take a new technique. 1. Score it on each axis. 2. Crunch the numbers to get a hardware and an ecosystem score. 3. Map those scores to one of the 4 friction zones. And then 4. You ask the single most important question. Can my team, with our budget and our timeline, actually afford to pay this friction tax? It gives you the scaffolding to make a really grounded decision.
All right, let's bring it all home. What does this friction map tell us about the future of AI and where things are headed?
You know, the sign of a really good framework is that it's not just a nice story. It makes concrete, testable predictions. And this one does. The source lays out 4 predictions that are designed to be falsifiable. For instance, it predicts that no pure state space model over 30 billion parameters is going to crack the top 10 on the Chatbot Arena leaderboard by the end of 2028. If these predictions turn out to be wrong, it means the map itself needs to be redrawn.
And this all leads to a really powerful, maybe even a little sobering conclusion, which is captured perfectly in this quote. The transformer doesn't need to be optimal. It just needs to be good enough and too expensive to escape. The economic friction is so high for alternatives that we just keep doubling down on the architecture we already have, making it even harder for anything else to compete. So this is the thought I want to leave you with. For anyone building into space, the game isn't about finding the most elegant architecture on a whiteboard. It's about a cold, hard look at the economic reality of the hardware you're running on. So don't fight the friction. Map it, price it, and then decide for yourself. What friction can you afford to pay?